Come let us drift for a moment. Picture in your mind a quiet corner of an unremarkable galaxy orbiting an average stable star. In this gentle swirl of space, a small rocky world is spinning. It is blue and white veiled in cloud, a precious point of light. This is our home, and it is when you truly stop to think about it, an absurd and beautiful miracle. We are a planet of rock and water, and yet we are aware. You are here listening to these words, a collection of atoms that has somehow learned to question its own existence. In a universe governed by chaos and the slow, inevitable march toward cold and darkness, a spark ignited here. We call it life. But how? How, in the unimaginable violence of a young solar system, did inert chemicals, simple minerals and raw energy conspire to create something that could feel and grow and wonder? This is the great riddle of abiogenesis, the puzzle of how non-living matter crossed the threshold into life. It is the story of a planet transformed from a sterile rock into a cradle. It begins not with a grand design, but perhaps in a very humble place. For decades, we have tried to imagine the setting for this transformation. We have sought the stage where the first act of life unfolded. One of the most enduring images was painted for us by Charles Darwin himself, who dreamed of a warm little pool. He pictured a small sun-drenched body of water rich with all the necessary ingredients, ammonia, phosphoric salts, light and heat, where a protein compound could form ready to undergo more complex changes. In the 1950s, two scientists, Stanley Miller and Harold Urey, tried to build this little pool in their laboratory. It was a brave and brilliant attempt to recreate the dawn of our world. They sealed water, methane, ammonia, and hydrogen gas in a closed system of glass flasks. To simulate the raw power of the young planet, they sent electric sparks, artificial lightning, crackling through the mixture. After just 1 week, the water, which had started clear, turned a deep murky brown. When they analysed this primordial soup, they found something astonishing: amino acids. These are the fundamental building blocks of proteins, the very girders and gears of life as we know it. The experiment was a revelation. It proved that from the simplest inorganic materials, the complex components of biology could arise naturally, spontaneously. But the surface of the young Earth may not have been so gentle. Perhaps the true cradle was not a sunlit pool, but a place of crushing darkness and extreme power. Some scientists believe life began deep in the ocean, miles beneath the waves, where no sunlight has ever reached. Here, the planet's crust is thin and seawater seeps down into the rock, where it is superheated by magma. This water, now scalding hot and saturated with dissolved minerals and gases like hydrogen sulfide, bursts back into the ocean through chimney-like structures we call deep-sea vents, or black smokers. In this dark, pressurized world, life would not be powered by the sun. It would be powered by the Earth itself. It would be a life built on chemosynthesis, the harnessing of chemical energy. These vents are oases in the deep-sea desert, teeming with bacteria and strange creatures that thrive on this geothermal energy. Perhaps these fiery, chemical-rich chimneys were the perfect protected laboratories, providing the intense energy and the mineral catalyst needed to force the first molecules together. Whichever stage is correct, the warm pool or the dark vent, the setting was profoundly alien. This was not the blue-green world we know. This was a young, chaotic planet. The sky was not blue. It was a hazy orange, thick with methane and carbon dioxide. The air was a toxic fog of ammonia and water vapor with almost no free oxygen to breathe. The oceans were iron-rich, perhaps a murky green. It was not a welcoming place, but it was the perfect chemical playground. It was a world waiting for its components to find each other. The experiment by Miller and Urey gave us the building blocks. But a pile of bricks is not a house. How did these simple amino acids and sugars begin to organize themselves? How did they form the long complex chains, the proteins and nucleic acids that life requires? The universe, it seems, provided a helping hand. The molecules were not just floating aimlessly in a vast ocean. They may have found a template, a scaffold to hold them in place. This scaffold might have been simple clay. Yes, the fine-grained mud at the bottom of a pool. Clay minerals have a peculiar structure. They are made of layered crystalline sheets. These sheets have a slight electrical charge and can attract and hold organic molecules, arranging them in precise, orderly rows. In these microscopic grooves lined up like beads on a string, the first simple molecules may have been encouraged to link together, forming longer, more complex chains. The clay acted as a matchmaker, a molecular mold that concentrated the ingredients and catalyzed the first crucial reactions. But this leads to one of the biggest paradoxes in biology. To build a living cell, you need instructions, a blueprint. In all life today, that blueprint is DNA, or deoxyribonucleic acid. But to read and copy that DNA, you need machinery. That machinery is made of proteins. Here is the riddle. You need proteins to read the DNA, but the instructions for building those proteins are on the DNA. It's the ultimate chicken and egg problem. Which came first? The answer may be neither. The solution may be a remarkable molecule that can do both jobs. This is the RNA world. Hypothesis. RNA, or ribonucleic acid, is DNA's simpler, more ancient cousin. We now know that RNA is not just a messenger, it is a multi-talented molecule. Like DNA, it can store information carrying a genetic code. But like a protein, RNA can also fold itself into complex three-dimensional shapes that allow it to act as a catalyst driving chemical reactions. RNA could have been the soloist that started the symphony, a single molecule that served as both the blueprint and the builder. This RNA world was a chemical revolution, but it was still missing one crucial element: a container. A masterpiece of RNA capable of copying itself would be useless if its creation simply floated away. Life needed a boundary, it needed an inside and an outside, it needed a self. This too the universe provided. The building blocks of life include molecules called lipids, fats, and lipids have a special relationship with water. One end is drawn to it, the other is repelled. When you mix them in water, they spontaneously automatically arrange themselves into tiny hollow spheres. They form bubbles. These lipid bubbles, simple fatty membranes, were the first protocells. They were not alive, but they were the vessels of life. They were the private rooms, the tiny laboratories, where these new self-copying RNA molecules could be trapped inside along with their chemical resources. This simple bubble created a private world concentrating the ingredients for life and protecting them from the chaos outside. This was the turning point. The moment a self-copying molecule like RNA became enclosed within a lipid bubble, something entirely new was born. This was no longer just chemistry, this was biology. The key was replication. This was the grandest leap, the moment a collection of molecules could create a copy of itself. With replication came inheritance, and with inheritance came error. Every time the RNA copied itself, it would make tiny mistakes, tiny variations. Most of these mistakes would be failures, but a few by pure chance would make the system slightly better at surviving or at copying itself faster. This was the dawn of evolution. The protocells that were more stable or more efficient at grabbing resources from their environment would thrive and multiply while others would fall apart. The first true cell was born. A line was drawn. Inside that membrane was a system that could sustain itself, that could react to its environment, and that could reproduce. This was the common ancestor of everything that has ever lived, from the simplest bacterium to the whale to the tree to you. And perhaps the most staggering part of this story is how quickly it all seems to have happened. Our planet formed about 4.5 billion years ago. For its first few 100 million years, it was a molten hell, a target for giant asteroids. But as soon as the planet cooled enough for liquid water to exist, as soon as the stage was set, life appeared. The oldest, most convincing fossils we have are nearly 3.5 billion years old. The evidence suggests that life did not wait. It emerged almost immediately in the geological blink of an eye. This astonishing speed forces us to ask the final profound question. We began by calling life a miracle, an absurd accident. But what if it isn't? What if, given a wet, rocky planet with the right chemical ingredients and a source of energy, life is not a miracle at all? What if life is inevitable? What if the universe is not just filled with sterile rocks, but is built to create complexity? What if life is a fundamental property of chemistry, a cosmic imperative just waiting for the right conditions to spark in the dark? We have journeyed together across the unfeeling, magnificent emptiness of space. We have watched stars ignite and die, scattering the dust of creation across the cosmos. Now let us bring our focus inward, down from the scale of galaxies to a single small blue-green world orbiting a quiet yellow star. Our world, Earth. It is young. The bombardment from space has slowed. The oceans are vast and warm, holding the chemical secrets brought here by comets and asteroids. And in that warm, quiet water, something impossible has happened. The universe, which for billions of years knew only physics and chemistry, has just produced biology. Life has begun. But if you were to visit this early Earth, you would see no movement. You would hear no sound. The land is barren rock. The oceans are still. There are no fish, no plants, no seaweed, no anything, not to our eyes. The planet seems to be sleeping, but this is not a sleep of emptiness. It is a sleep of profound, slow, patient creation. For the next 2 billion years, perhaps even 3 billion years, the planet belongs entirely to the invisible. This is the long quiet dawn, the age of bacteria. For a stretch of time that our minds cannot truly hold 2 billion years, nothing happens, nothing changes, at least not in a way we would recognize. Life is a single microscopic cell. It floats. It senses the chemicals in the water around it. It finds food. It divides. It becomes 2, 2 become 4, 4 become 8. This world has no eyes. It has no minds. It has no fear or love or ambition. It is a planet operating on the most basic fundamental drive to continue, to be. These simple cells, these prokaryotes, are the foundation. They are the great ancestors of everything that will ever live. They are in the soil, in the water, in the air. They are the unseen architects of the planet. For all this time, the sky is not blue. It is perhaps a pale orange or a reddish brown, thick with methane and carbon dioxide. The oceans are not blue, but a murky greenish brown rich with dissolved iron. It is a truly alien world, and yet it is teeming with life, a silent, patient, planetary hum of replication. These tiny beings are not just waiting, they are experimenting. In the deep, dark trenches of the ocean, by boiling volcanic vents, they are learning to eat sulfur. In the sunlit, shallow waters, they are learning to eat light. One of these bacteria, a type we now call cyanobacteria, perfects this new magic. It learns to take sunlight, water, and carbon dioxide and turn it into energy. It is a revolution. This new process, photosynthesis, is so successful that these bacteria spread across the entire globe. They become the first great green-blue scum covering the surface of the ancient oceans. They are thriving, and as they thrive, they release a waste product, a gas that is to the rest of life on Earth a deadly corrosive poison. This gas is oxygen. For millions of years, the planet tried to absorb this new poison. The oxygen released by the bacteria immediately combined with the iron in the oceans. The seas began to rust. Over eons, this iron oxide, this rust fell to the ocean floor as sediment, creating the vast, banded iron formations that we now mine for our own industries. The planet was desperately trying to bury this toxic gas, but the bacteria were too successful. Eventually, all the iron in the oceans was rusted. The poison had nowhere else to go. It began to build up, leaking out of the water and into the atmosphere. The Great Oxidation Event. It was the first and perhaps the greatest pollution crisis in Earth's history, and it triggered the world's first mass extinction. Life on Earth had grown up in an oxygen-free world. This new gas ripped apart the delicate chemistry of the cells that encountered it. It was a global apocalypse. Entire ecosystems of these ancient bacteria which had ruled the world for billions of years were wiped out. They were poisoned by the breath of their own cousins. The new oxygen in the air also reacted with the methane, a powerful greenhouse gas, and neutralized it. The planet's warm blanket was suddenly torn away. The temperature plummeted, the world froze. This was the snowball Earth, a planet locked in ice perhaps for hundreds of millions of years. Life itself was almost extinguished. It clung on in tiny warm pockets, perhaps near volcanic vents, or in patches of unfrozen sunlit water. It seemed that life's grand experiment was over, killed by its own success. But life does not end, it adapts. Perhaps, in the crucible of this frozen, poisoned world, a new kind of life was being forged. Some bacteria hiding in the dark had evolved a new trick. They had learned to use the poison, they learned to breathe, they developed a process that could take this reactive oxygen and use it to burn their food, releasing far more energy than any other process before. The world was now divided. There was the old life hiding from oxygen in the mud, and there was the new life breathing oxygen and unlocking a new powerful energy. And then after another billion years of this cold, slow stalemate, the second great miracle happened. It was not an invention, it was an accident, a merger. We believe one larger cell itself simply tried to eat a smaller bacterium. Perhaps it was one of these new oxygen-breathing bacteria. But for some reason the larger cell did not digest it. The smaller cell survived living inside its predator. This was not an invasion, it became a partnership. The large cell provided a safe home, protecting the smaller cell from the outside world and bringing it food. In return, the small cell, the guest, did what it did best. It breathed. It took the food from the host cell and used oxygen to burn it, releasing a flood of pure, clean energy. So much energy that the host cell had power to spare. This internal living power plant is what we now call the mitochondrion. This new combined being a cell within a cell was the first eukaryote. This is perhaps the single most important event in the history of our own lineage. This is the moment that we began. Every animal, every plant, every tree, every mushroom, every creature on Earth that you can see with your naked eye, we are all eukaryotes. We all share this ancient ancestor. We all carry these tiny captured bacteria within every single one of our cells, breathing for us, powering our thoughts, our movements, and our dreams. When we look at the stars, we often wonder about the Great Filter. That is the idea of a challenge or a step so difficult that most life in the universe fails to pass it. We wonder if it is the leap to technology or interstellar travel. But perhaps the Great Filter is this. Perhaps the universe is filled with worlds like our early Earth covered in a simple bacterial slime. But perhaps this accident, this merger, this creation of a complex cell from the fusion of two simple ones is so impossibly rare that it almost never happens. Perhaps the hardest step in the entire universe is not learning to build a spaceship, but learning by pure chance how to truly cooperate. This new eukaryotic cell had a budget. It had an economy of energy. It had so much power it could afford to do new things, it could build new complex parts, it could afford to experiment, and most importantly, it could afford to work with others. These new cells, fat with energy, could stick together after dividing. They could share resources. They could begin to specialize. One cell could focus it on movement, another on sensing the environment, another on digestion. The foundation was laid. Life had moved from a single note to the first chord. The silent, sleeping planet which had dreamed for 3 billion years in the key of simple was finally ready to wake up. It was ready to build a body. It was ready to build us. For the last part of our journey, we have been soaring through the infinite, looking at the grand tapestry of the cosmos. We've seen the spiral arms of galaxies glittering with the light of 1 trillion suns. We have imagined the unimaginable number of worlds orbiting those suns. We have felt a sense of wonder, of awe, of boundless possibility. But now, let's pause. Let's stop our journey outward and just be still, here in the quiet darkness. And let's listen. Let's use our planet's largest ears, the giant radio telescopes we have built pointed at the heavens. Let's listen for a signal, a pattern, a whisper, a simple hello from across the void. What do we hear? There is the gentle ancient hiss of radiation left over from the Big Bang, the static of creation itself. There is the steady rhythmic pulse of distant stars, the natural heartbeat of the cosmos. But from all those billions and billions of worlds, there is only silence, a deep, profound and unsettling quiet. This silence brings us back to Earth. It brings us back to a simple everyday moment. A warm, sunny day in the summer of 1950. A group of brilliant physicists were walking to lunch discussing the exciting new mathematics of space travel and the possibility of other older civilizations in the galaxy. One of these men was the famous scientist Enrico Fermi. He listened quietly to all the grand speculation, and then suddenly he asked a question. A question so simple, so obvious that it stopped the conversation cold. A question that still echoes unanswered decades later. He just looked up at the sky and asked, "Where is everybody?" The tension. This is the heart of the paradox. It is a tension, a deep contradiction between two ideas that both seem completely true. The first idea is the math. Let's just think about our own galaxy, the Milky Way. We estimate it contains somewhere between 200 billion and 400 billion stars. That number is so large it's hard to even picture. We now know, thanks to our powerful telescopes, that most of those stars have planets. Not just a few, most of them, billions upon billions of worlds. Many of those worlds are the right size, similar to Earth. And many are in what we call the habitable zone, the perfect distance from their star, not too hot and not too cold, where liquid water could flow in rivers and pool in oceans. The ingredients for life as we know it are everywhere. Now add the ingredient of time. The universe is very old, almost 14 billion years. Our solar system is a relative newcomer at only about 4.5 billion years old. Life on Earth started almost immediately, as soon as the planet was cool enough, it seems eager. If the ingredients are everywhere and life is eager, it must have started in many other places. And if it started in those other places, it must have had time. Lots of time. Imagine a civilization that is just 1 million years older than we are. Think about what we have done in just 100 years. We went from our first powered flight to walking on the moon. We developed computers and global communication. What could a civilization do with 1 million years? Or 10 million or 1 billion? They would have solved interstellar travel. They would have spread across the galaxy, perhaps leaving signals or building massive structures, or just being there. The galaxy should be loud. It should be a vibrant, bustling place, humming with the activity of countless civilizations, as obvious to us as a major city lit up at night in the middle of a dark forest. That is the first idea. The math says the galaxy must be full. The second idea is the reality. We look, we listen, we search, and we find nothing. Not one verified signal, not one hello, not a single trace of an artifact or a ship or a giant structure. The stars are silent. The universe, as far as we can tell, is empty. This is the tension. The numbers shout that life must be common. Our observations whisper that we are completely alone. Both of these cannot be true. So where is the mistake in our thinking? Introducing the Great Filter. This question, this paradox, has forced us to consider a dark and very sober possibility. Perhaps there is a reason the galaxy is so quiet. Perhaps there is a barrier, a challenge, a test. This idea is known as the Great Filter. The theory suggests that on the long evolutionary path from a simple non-living chemical on a damp planet, all the way to an advanced spacefaring civilization that can communicate across the stars, there is a wall, a filter, a point where almost every single form of life everywhere in the universe fails the test. It hits this barrier and it goes extinct. This is why the galaxy, as said about everyone, fails. This leads us to the most important and perhaps the most terrifying question of all. Where is this Great Filter? When we look at our own history, where does this wall lie? Is it behind us? Or is it in front of us? Think about that. If the filter is behind us, we are the miracle. We are the first. It would mean that the hardest step is over. Maybe the filter was the origin of life itself. Perhaps the jump from non-living matter to the first living cell is so unbelievably bare that it has only happened once. Here. Or maybe the filter was the jump to complex life. Maybe the universe is full of simple bacteria, but the accident that created complex cells, the kind that build plants and animals, is the 1 in a trillion miracle. If that is true, then the silence is understandable. The cosmos is empty because we are the first. The universe is ours. But what if the filter is not behind us? What if the filter is still to come? This is a much more chilling thought. It would mean that life starts all the time, all over the galaxy. It evolves, it becomes complex, it even becomes intelligent. But then something always stops it. Perhaps technology is the filter. Perhaps every intelligent civilization eventually discovers a power it cannot control, like nuclear weapons or artificial intelligence or a new law of physics, and it destroys itself. Every single time. If this is true, then the silence of the galaxy is not a promise. It is a warning. It means we are not the first, we are just next. We are racing toward the same wall that every other civilization has hit. When we look out at the deep silent cosmos, are we looking at our future? Are we seeing the ghosts of all those who came before, who reached this exact point and who failed to pass the test? The silence then means our own test is coming soon. So where do we look for this great stone barrier? The most comforting and in some ways the most terrifying possibility is that the Great Filter is already behind us. Think about that. What if the hardest part of the journey is over? What if in the long cosmic obstacle course of life our planet has already cleared the highest hurdles? If this is true, it changes everything. It means we are not just ordinary, it means we are rare, perhaps impossibly rare. We are the victors of an evolutionary lottery that almost no one wins. If we are the winners, what then was the filter? Where was the test that everything else failed? Perhaps the filter was the very beginning, the first great step. We call it a biogenesis. It's a scientific word, but it describes a moment of pure magic. It is the moment that non-living chemistry blinked and became biology. It is the instant that a random collection of molecules, some carbon, some water, some minerals warmed by a young sun, stopped just being stuff and became the first living thing, the first cell, the first entity that could eat and grow and most importantly replicate. We look around our own world and life seems easy. It is unstoppable. It thrives in the boiling acid of volcanic vents and in the absolute darkness of the deepest ocean trenches. It clings to ice and floats in the clouds. It seems inevitable. But this is an illusion of perspective. Every single living thing we have ever found, every human, every whale, every bird, every tree, every tiny bacterium shares a common ancestor. It is all part of one single family tree. This suggests that on planet Earth this miracle happened exactly once. In 4.5 billion years it happened one time. Scientists have tried to recreate this moment. We can mix the primordial soup in a laboratory, we can add electricity to mimic lightning, and we can create the building blocks of life like amino acids. But we have never ever created life itself. We have never seen the spark jump from chemistry to biology. We don't even know how it happened. What if that is the Great Filter? What if the universe is filled with beautiful, perfect planets Planets with stable orbits, gentle sunlight, and vast liquid water oceans. Worlds that have every single ingredient for life, a rich chemical soup simmering for billions of years, but the spark just never happens. The cosmic lottery ticket is never drawn. Imagine that for a moment. Countless worlds, silent and sterile. The oceans stir, the winds blow, but nothing ever wakes up. If this is the filter, then the silence we hear in the cosmos is not the silence of a graveyard filled with civilizations that have died. It is the silence of a nursery that has always been empty. It would mean that we are quite literally a miracle, the only ones who woke up. But what if that's not the filter? Let's be generous. Let's say the spark of life is actually common. Let's imagine the universe is teeming with life. Thin film of bacteria on countless worlds, a green or purple algae floating in 1 trillion alien seas. The galaxy in this case would be pulsing with simple single-celled life. This would be an incredible discovery, but it would still be a very quiet universe. There would be no one to talk to, because there is another, perhaps even greater hurdle. The filter might be the leap from simple life to complex life. Let's look at our own history again. Life began on Earth very early, perhaps almost 4 billion years ago. But for the next 3 billion years, nothing much happened. Imagine our planet for 3 billion years. Life was everywhere, but it was just slime. It was a world of bacteria. There were no plants, no fish, no animals, no eyes, no brains, no hearts. For a period we sometimes call the boring billion, life was stuck. It was successful, it was widespread, but it was not complex. Then something happened. An event so rare we think it also happened only one time. A simple cell tried to eat another smaller cell. But instead of being digested, the smaller cell stayed. It survived inside the larger one. They formed a partnership. The little cell became a tiny energy factory for the bigger cell. This new combined complex cell is what we call a eukaryote. This single accidental merger, this ghost in the machine, is the ancestor of everything you can see with your naked eye. Every mushroom, every insect, every blade of grass, and every human being. We are all the descendants of that one singular accident. What if that is the filter? What if the universe is a microbial mat? What if it is a galaxy overflowing with simple bacterial life, but the leap to complexity, the leap to cells that can work together to build a body, a leaf, a fin, or a brain, is the step that almost no one ever makes. The cosmos could be alive, but it might not have any minds to look back at it. No one to build a telescope, no one to compose a symphony, no one to feel wonder. Just vast silent oceans of bacteria waiting for a spark of complexity that never ever comes. Now let us breathe and truly consider the implication. If the filter is behind us, if the hard part was starting life or starting complex life, what does that mean for us? Here, now. It means we are the first, or at the very least we are one of the first. It means we are the ones who made it. We are the survivors. We are the universe's first conscious attempt to understand itself. When you look up at the night sky, that immense crushing silence is not an absence. It is a stage that has been waiting empty for billions of years for an actor to walk onto it. If we are alone, it means that all the beauty, all the capacity for joy, all the art, all the love, all the curiosity, and all the meaning in the cosmos rests only with us, right here, on this one small fragile blue world. It is not a lonely thought, it is a staggering one. It is an awesome one. It gives our lives a new and profound purpose. It means that all the value in this vast cold universe, as far as we know, is not out there. It is in here. It is created by us. It is in our minds and in our hearts. If the great filter is truly behind us, then we are not just another species on another random planet. We are the bearers of a precious singular flame. We are the mind of the cosmos. And that places a profound, almost sacred responsibility upon our shoulders. A responsibility to endure, to grow, to protect this one single spark of consciousness, to cherish it, and to not through our own carelessness or anger snuff it out. Because if we do, the universe might return to that silent, unthinking state, and this time it might be forever. And so we stare into that vast, silent night and we ask, where is everybody? This question, the great paradox of our time, casts a long shadow. And within that shadow, a chilling idea has taken root. A concept known as the Great Filter. Imagine the development of life as a long, dark hallway with a series of doors. To get from the first spark of non-living matter to a starfaring galactic civilization, you must pass through every single door. A filter is one of these doors, but it's a special kind. It's a door that is almost impossible to open. It could be the leap from simple cells to complex ones. It could be the jump to tool-using intelligence. Or it could be something we have not yet faced. The chilling possibility is that this filter, this great barrier, is not behind us but ahead of us. This implies the universe isn't silent because life is rare. It's silent because intelligent life does not survive. Think about our own journey. We have risen so quickly from chipping stones to splitting atoms in the blink of a cosmic eye. But this very intelligence, this gift that allows us to understand the stars, may be a self-limiting one. We build tools of incredible power, and with them we gain the capacity for incredible self-destruction. It's a tragic irony. The same drive that pushes us to innovate, to explore and to grow is often entangled with competition, fear and a thirst for control. Progress and risk, it seems, are two sides of the same coin. The moment a civilization discovers the energy locked inside an atom, it simultaneously hands itself the key to a brighter future and a loaded gun. We can see the shadows of this filter forming on our own walls. We see it in the thousands of nuclear weapons that sleep in their silos. A planetary nightmare just a few bad decisions away. We see it in the slow creeping changes to our climate, a problem born from the very success of our industrial civilization. And we see it in the new frontiers of artificial intelligence, a creation we are building with astonishing speed, without fully understanding the mind we are trying to light. Perhaps this is the answer to the silence. Perhaps every emerging intelligence reaches this critical point, this tightrope walk over an abyss. And perhaps almost no one makes it to the other side. The galaxy could be a graveyard of civilizations that flowered, discovered, and then in a final brilliant flash of their own making were extinguished. When we listen for an echo, we hear only the wind blowing over ruins. But what if the filter isn't our fault? What if the threat isn't from within, but from without? The universe, for all its beauty, is not a gentle place. It is a realm of unimaginable violence. It's an arena of cosmic inevitabilities. We tend to think of our solar system as a safe harbor, but on a galactic timescale it is anything but. Imagine a gamma ray burst the death cry of a massive collapsing star. This burst is a focused beam of energy so powerful that if it were to strike our planet even from thousands of light years away, it could scour the atmosphere, shred the ozone layer, and trigger a mass extinction that resets the clock on complex life. It happens without warning. It is unstoppable. Or consider a nearby supernova, the explosion of a star that briefly outshines its entire galaxy. The wave of radiation and high-energy particles would be catastrophic, sterilizing entire regions of space. These events are not rare. They are a regular, scheduled part of the galaxy's life cycle. In this version of the filter, the universe is a garden that is periodically and ruthlessly weeded by cosmic fire. Life might be sprouting everywhere all the time, but before it can reach intelligence, before it can build radios and look up a cosmic event, simply resets the board. Maybe the silence isn't a graveyard, but a nursery constantly being hit by frost just as the seedlings are about to grow. This would mean that survival isn't a test of intelligence or wisdom, it's a game of cosmic luck. Perhaps we are simply in a lucky bubble, a quiet pocket of the galaxy that has been left alone long enough to allow a creature like us to sit by a fire and wonder about it all. It's a humbling thought, isn't it? That our existence might hinge on nothing more than a fortunate position in space and time. All of this, the self-destruction, the cosmic resets, it all feels so heavy, so profound, and yet we must anchor ourselves with one simple critical truth. We are working with a data set of 1. In science, we call this the n=1 problem. N is the number of examples we have to study, and for intelligent technological life our n is just 1, us. We are a single data point in a cosmic graph of unknown size. Everything we have just discussed, the paradox, the filters, the self-destruction, the gamma ray bursts, is speculation. It is an attempt to draw a universal law from a single example. It's like trying to understand all the forests on Earth by looking at a single tree. Is our tree typical? Is it the exception? Are we the first to grow this tall? Or are we the last one standing in a forest that has been clear-cut? We simply do not know. When we look at our own history, we see a path full of improbable twists and lucky breaks. If that asteroid hadn't struck, would dinosaurs be building radios today? If our moon wasn't so large, would our stable climate have ever allowed complex life to flourish? This n=1 problem is the ultimate source of humility. It reminds us that our story is the only one we know. We project our own fears of war, of climate change, of our own technology onto the cosmos. We see in the silence a reflection of our own anxieties. But the truth is, we don't know what the rules of the game are. We are a species that has just woken up in the dark trying to guess the size and shape of the room based on the single patch of floor we are standing on. And so we are left with the most profound question of all, this great filter. This barrier to galactic civilization, is it behind us or is it in front of us? If the filter is behind us, if the truly hard step was the origin of life itself or the leap to a complex cell, then we are the victors. We have won the cosmic lottery. It would mean that we are impossibly miraculously rare. It would mean the silence is empty because we are the first or perhaps the only to have made it this far. The universe is a vast open frontier and it is ours to explore. It places a beautiful, terrible responsibility upon our shoulders to be the guardians of the only consciousness that exists. But if the filter is the head of us, then the silence is a warning. It's the silence of the graveyard. It means the universe was or is full of hopeful civilizations just like ours. Civilizations that looked up at their stars just as we do, and wondered. Civilizations that built and dreamed and then reached the same tightrope that we are on right now, and they fell. If this is true, then we are not the first, we are simply the next in line to face the test. We are approaching the Great Barrier, and the silence of the cosmos is the deafening sound of all those who failed to pass. This is the shadow on the wall, a mystery that is not just about them, but about us. Our future may be written in that vast, beautiful emptiness. The question is, can we learn to read it? In our boundless journey, we have cast our gaze so far into the deep looking for a shimmer of light from a world that might be like ours. We've sifted through the noise of the cosmos, hoping to overhear a whisper, a signal, a sign that we are not the only ones asking these questions. We have built giant eyes to look for where life could be. But what if in our eagerness to map the distant stars we overlook the most vital lesson? What if the universe has been trying to tell us something not just about where to look, but how to look? What if the rules for life, the ones we wrote ourselves, were wrong? This is the great shift in our thinking. It has a name, astrobiology. It's the beautiful, simple marriage of the stars and of life itself. It doesn't just ask, where is life? It asks, what is life? What are its absolute fundamental limits? And as we've begun to explore the hidden corners of our own world, we've found that the limits we set were just our own. We defined life by what we need: gentle sunlight, fresh air, a comfortable temperature. We imagined life as a delicate, fragile thing. But Earth itself has shown us life is not delicate. Life is stubborn. It is a relentless, creative and powerful force, and the proof is in the organisms we call extremophiles. It's a perfect name, lovers of the extreme. These are not creatures just surviving in the harshest places on Earth. They are thriving. Think of the boiling, acidic hot springs of Yellowstone. The water is corrosive enough to dissolve metal, and yet it is teeming with microbes painting the rocks in vibrant, living colours. Think of the absolute darkness miles down at the bottom of the ocean. The pressure is immense enough to crush a human instantly. We thought it was a sterile, dead desert. Then we found the hydrothermal vents gushing superheated, mineral-rich water, and clustered around them in total darkness is a whole ecosystem. Giant tube worms, pale crabs, all living on bacteria that eat chemicals, not sunlight. They breathe sulfur. We have found life in the dry valleys of Antarctica, a place so cold and barren, it's the closest we have to the surface of Mars. We have drilled miles deep into the ancient ice, into lakes that have not seen the sun in millions of years, and found microbes living, slowly but living. There is life inside solid rock miles beneath our feet. There is life in pools of acid. And astonishingly, there is life inside the cooling pools of nuclear reactors, places flooded with radiation so intense it should tear a creature's DNA to shreds. This brought us to one of the most incredible beings we know, Deinococcus radiodurans. It's a bacterium so tough scientists call it Conan the Bacterium. It can withstand thousands of times the radiation dose that would kill a human. You can blast it, you can dry it out completely until it shatters, and it will just wait. Add a drop of water and its broken pieces of DNA pull themselves back together. It rebuilds its own genetic code from hundreds of fragments perfectly and simply, continues living. When we discovered these extremophiles, the rulebook for life was torn apart. Life didn't need our gentle sun. It didn't need our comfortable air. It just needed three things: liquid water, a source of energy, and the basic chemical building blocks. And with this new, simpler checklist, we were forced to look at our own solar system again. Not as a collection of dead rocks, but as a place of possibility. We had always dismissed the outer worlds, too cold, too dark, too far from the sun. The habitable zone, we called it, that narrow, perfect band where Earth orbits. But the extremophiles taught us that the sun isn't the only source of energy, and this new understanding turned 2 small frozen moons into the most exciting places in the entire solar system. Let's travel out past Mars, past the asteroid belt to the domain of the giant planet Jupiter. Let's visit its moon Europa. From the outside, it's an ice-covered ball, cracked and scarred. It's bitterly cold. But beneath that frozen shell, that crust of ice, many miles thick, our instruments have given us a clear signal. There is an ocean, a global ocean of liquid salt water that may contain more water than all of Earth's oceans combined. How can it be liquid so far from the sun? The answer is Jupiter. Europa is constantly squeezed and flexed by the immense gravity of its parent planet. It's like clenching a rubber ball in your hand over and over. This constant motion, this tidal friction generates heat. It warms Europa from the inside out, keeping that vast hidden ocean liquid. So we have water. What about energy and chemicals? That internal heat means Europa's ocean floor is almost certainly volcanic. It likely has hydrothermal vents, just like the ones on Earth, where we found those strange sunless ecosystems. Imagine it a vast, dark, warm ocean shielded from radiation by a thick roof of ice, and rich in minerals from its active seafloor. If you were to design a place for life to hide in the outer solar system, you would design Europa. Now let's journey a little further to the planet with the beautiful ring Saturn. Let's look at one of its smallest moons, a tiny speck of white ice called Enceladus. Enceladus is small, only about as wide as England. But in 2005, the Cassini spacecraft saw something that changed everything. Geysers, giant plumes of water ice and gas erupting from cracks near the moon's south pole, and blasting hundreds of miles out into space. Enceladus is spraying its own ocean into the void, and Cassini flew right through those plumes. It tasted them, and what it found was a revelation. It found water. It found salts, which tells us the water is liquid and in contact with a rocky core. It found organic compounds, the complex carbon-based molecules that are the building blocks of life. And most importantly, it found molecular hydrogen, H2. Why is that the jackpot? Because here on Earth, in those deep ocean vents, there are microbes whose favourite food is hydrogen. They eat hydrogen and exhale methane. It's the energy source that powers their entire food web. Finding hydrogen in the plumes of Enceladus is like finding a packed lunch in space. It is quite literally a potential food source for life as we know it. These 2 small moons have broken the last of our rules. They tell us you don't need a sun, you don't need a surface, you can have a vast, active and habitable world in the dark, cold depths of space, warmed only by the gravitational pull of its planet. The search for life is no longer just about looking for distant green and blue planets. It's about looking for these dark oceans, these hidden worlds. The possibility that life in all its stubborn glory is right here, right now, our next-door neighbour waiting to be discovered, just beneath a shell of ice. And so we look up at those faint lights in our own sky and we wonder, what things are swimming in those dark, ancient alien seas? And so we bring our focus closer to home, or rather we look for other homes. After soaring through the magnificent, sprawling structures of galaxies, we now zoom in, past the nebulae, past the clusters to the individual points of light that fill our night sky. We used to look up and see only stars. Now when we look, we see solar systems. We have learned in just the last few decades a staggering fact: almost every star you see is likely a sun to its own family of planets. The universe is teeming with worlds, but how do we find them? These tiny dark specks, light years appear, lost in the glare of their parent stars. It requires a kind of patience, a celestial detective work. One of our cleverest methods is to simply watch and wait. We stare at a star unblinking and look for a tiny rhythmic dip in its brightness. This is the transit method. It's the faint shadow of a planet as it passes in front of its star from our point of view. Imagine trying to spot a tiny moth flying in front of a brilliant spotlight that is miles and miles away. That is the level of precision we have achieved. We can see the shadow of a world. There is another way just as subtle. We look for a wobble. A planet, even a small one, has gravity, and as it orbits its star, its gravity pulls on the star just a little. It's like a tiny, unseen partner in a dance, causing the massive star to wobble back and forth by a minuscule amount. We can't see the wobble directly, but we can see its effect on the star's light. As the star moves slightly toward us, its light shifts ever so slightly blue. As it moves away, it shifts ever so slightly red. It's a rhythmic pulse in the starlight, a heartbeat that tells us an unseen companion is there. Through these methods, a shadow and a wobble, we have found thousands, a whole new catalogue of worlds. Naturally, our first question is, are any of them like Earth? This leads us to a concept we call the habitable zone. You may have heard it called the Goldilocks zone. It is that orbital ring around a star that is not too hot and not too cold, but just right. It is defined as the region where temperatures would allow liquid water to exist on a planet's surface. Liquid water. This is our great guiding star in the search for life. As far as we know, here on Earth, every living thing requires it. It is the solvent, the medium, the cradle for the complex chemistry of life. So we hunt for worlds in this special temperate zone, but we must be humble about this idea. The habitable zone is a useful guide, a place to start looking, but it is not a final answer. A planet's story is written by more than just its distance from its sun. A planet could be in the perfect zone, but have a thin atmosphere that lets all its heat escape, leaving it a frozen desert. Or it could be far outside the zone in the cold darkness, but be kept warm by a thick insulating blanket of an atmosphere like a greenhouse. Or like moons in our own solar system, a world could be heated from within by the constant gravitational squeezing of a giant parent planet, creating vast hidden oceans beneath a crust of ice. The habitable zone is a good idea, but the universe is almost certainly more creative than we are. Still, it has helped us find some incredible candidates. Let's imagine visiting just two. First, there is a world we call Kepler 42b. We sometimes call it Earth's older cousin. It orbits a star very much like our own sun, and it orbits in that cozy habitable zone. It is a super-Earth, meaning it's larger and likely heavier than our own world. What would it be like to stand there? The pull of gravity would feel stronger, weighing you down. The sky might be different, perhaps thicker veiled in clouds from a larger ocean. This world is also much older than Earth by more than 1 billion years. It makes you wonder, what has it seen? If life ever began there, what forms has it taken over such a vast, deep span of time? And then there is Proxima b. This one is special because it is our next-door neighbour, the closest exoplanet to us. It orbits the star Proxima Centauri just over 4 light-years away. If we could ever travel to the stars, this would be our very first stop. This planet is also in its star's habitable zone, but its star is nothing like our Sun. It is a small, dim and cool star known as a red dwarf. To stay warm, Proxima b must huddle incredibly close. But this closeness comes with a terrible danger. Red dwarfs are violent and stormy, especially in their youth. They erupt with massive solar flares, lashing their nearby planets with intense radiation. Proxima b is bathed in this fury. Is it a sterile, scoured rock? Or could life be tenacious? Could it be hiding deep beneath the planet's surface, or in a deep ocean sheltered from the stellar rage above? It's a tantalizing, frustrating mystery right on our cosmic doorstep. These discoveries are forcing us to broaden our imagination, to expand what the word habitable even means. We are starting to think beyond just rocky worlds that look like Earth. Scientists have proposed the existence of Hycean planets. These are fascinating. They are not like Earth at all. They are large worlds, perhaps bigger than Neptune, with thick, crushing atmospheres made mostly of hydrogen. And beneath that thick gas, they might host a truly global planet-wide ocean of liquid water. Life might not exist on a sunny surface, but in that deep, dark, pressurized water, feeding on chemicals, a very different kind of biology. And we must also consider planets that are tidally locked. Around small red dwarfs, this is common. The planet stops spinning relative to its star. One side faces the star forever in a state of eternal, scorching day. The other side faces away in a state of endless, frozen night. Where could life exist on such a world? Perhaps in the middle. There would be a ring, a twilight zone that circles the planet, a place of permanent sunrise or permanent sunset. Imagine living on a world where the red sun never moves, hanging forever at the horizon, casting shadows that are eternally long. This is what the search for exoplanets is truly doing. It is not just about finding a mirror of Earth, it is about dissolving our old assumptions. It's a lesson in possibility. Each new world we find, whether it's a hot Jupiter, a super-Earth, or a water world, is a new chapter in the universe's storybook, and we're just learning how to read it. Each discovery reminds us that the universe is not just stranger than we imagine, it is stranger than we can imagine. And somewhere in that vast catalogue of worlds, a new kind of dawn might be breaking. Here is the continuation of the script following your outline and stylistic requests. Imagine a giant curved dish, larger than a sports stadium nestled in a remote valley. It is not looking at the stars but listening to them. This is a radio telescope, one of many that make up humanity's great collective ear. For decades, we have pointed these giant instruments at the sky, patiently listening. We are cupping our ear to the cosmos, straining to hear a whisper. This is the search for extraterrestrial intelligence known as SETI. It is an act of profound, patient hope. We are not listening for the hum of a pulsar or the hiss of ancient radiation left over from the Big Bang. We are listening for something else, a pattern, a sequence that breaks the natural static, a signal that could not be made by a star or a galaxy, but only by another mind. We are listening for a hello from across the wilderness of space. We have been listening for a long time, and what we have heard so far is an overwhelming, profound silence. This isn't just quiet, it's what scientists call the loud silence. It is a silence that rings with implications, with questions that echo in our own minds. Our galaxy alone has billions of planets. Many of these planets are billions of years older than Earth. If life is common and if intelligence follows, the sky should be full of signals. It should sound like a bustling cosmic city with conversations echoing from star to star. But all we hear is the wind and the static. Where is everybody? This question haunts us. Why the silence? The possible answers are as vast as the space we are searching. Perhaps we are simply listening incorrectly. Imagine trying to use an old AM radio to pick up a modern Wi-Fi signal. We are scanning for specific types of radio waves, but what if advanced civilizations use something else entirely? Perhaps they communicate with focused lasers or with particles we have not yet discovered, or in a dimension we cannot yet access. We might be listening to the wrong station on a cosmic dial that has trillions of channels. Another possibility is that they have gone silent, but not in the way we think. Our own signals are messy. Old analog television broadcasts radiate out into space, shouting our existence to the stars. But our modern signals are different. They are digital, compressed, and efficient. They are designed to go from point A to point B, not to be broadcast to the entire galaxy. An efficient signal to an outside observer looks almost identical to random natural noise. Perhaps the galaxy is talking, but everyone is whispering in these efficient digital streams, and we are still listening for a loud analog shout. And then there is the final, most chilling possibility, the one we think about in the quiet of the night. Perhaps the silence is loud because there is no one else to talk. Perhaps life is common, but intelligent technological life is impossibly rare. Or perhaps civilizations rise, discover the laws of physics, and then invariably use that knowledge to destroy themselves before they can ever reach the stars. Perhaps we are the first, or perhaps we are the last. This is the great heavy question at the heart of the SETI search. This deafening silence has led us to a second, perhaps more practical great search. If we cannot hear a whisper, perhaps we can find a breath. This is the search for biosignatures. It is a new and revolutionary approach. We are no longer just listening for intelligence. We are looking for life in any form. Even if it's just a simple layer of algae on a distant world, it would change our understanding of the universe forever. This search does not require us to guess at alien psychology or technology. It only requires us to understand the laws of chemistry and biology. We are not searching for a hello, we are searching for the simple chemical evidence of a living world. How do you find life from light years away? You look for a planet that is chemically out of balance. A dead planet left on its own will settle into a state of chemical stability. Everything reacts until it can react no more. But life is a force of chaos. Life pollutes. It consumes, it breathes, it excretes, and in doing so it fundamentally changes the air around it. On our own world, our atmosphere is filled with a highly reactive, unstable gas, oxygen. Without life, without the trillions of plants and algae constantly breathing it out, this oxygen would quickly vanish. It would react with the rocks and the oceans and be gone. At the same time, life produces other gases like methane. Finding large amounts of both oxygen and methane in the same atmosphere is a powerful clue. These two gases on their own should destroy each other. To find them coexisting is a sign of a deep chemical imbalance. It suggests that some active, powerful process is constantly pumping both of them into the air. That active process could very well be life. It is the chemical signature of a living, breathing planet. But how do we read the air of a planet orbiting a star hundreds of light years away? This is where our new generation of great observatories like the James Webb Space Telescope becomes so powerful. When a distant planet passes in front of its star from our point of view, a tiny, tiny sliver of the star's light filters through the planet's atmosphere. The telescope can catch this light. Different molecules in the atmosphere absorb different colors of light, leaving a unique barcode or fingerprint on that light. By reading this barcode, we can tell what the air on that world is made of. We can look for the telltale signs of water, of carbon dioxide, and yes, of that potent combination of oxygen and methane. For the first time in human history, we are capable of reading the atmosphere of another world. This search, however, is filled with challenges. The universe is clever, and we must be cautious. What if a non-living geological process gas could also create oxygen? What if a planet's water is broken apart by harsh starlight in just the right way to mimic the breath of life? These are called false positives, and they are the great fear of every scientist in this field. Finding oxygen would be historic. But finding it and proving it came from life and not from some strange dead geological process is the true challenge. We must be patient. We must be skeptical. We must be sure that the breath we detect is truly the breath of life and not just a geological sigh from a lonely empty world. So we come to it at last. After all our wandering through nebulae and galactic clusters, after listening to the whispers of dying stars, we find ourselves standing before a mirror. And that mirror is the great, profound cosmic silence. We have looked out so far, and in the end, we are forced to look back at ourselves to ask the most human question of all. What does this silence mean? Is it a sign of our uniqueness or a warning of our future? We try to find an answer in numbers in what we call probability. We have one data point and one only Earth. Here, life didn't wait billions of years to get started. It seems to have appeared almost instantly as soon as our planet cooled enough to hold liquid water. The ink was barely dry on the planet's formation, and life was already writing its first chapter. There is a way of thinking a logic called Bayesian analysis that takes this simple fact very seriously. It suggests that if something happens very quickly when the conditions are right, it probably isn't an incredibly difficult or rare event. Imagine trying to start a fire with damp wood. If it catches flame on the very first strike of the match, you would probably guess that the wood wasn't as damp as you thought. Perhaps the jump from simple chemistry to simple life is the same. Perhaps it's a common, almost inevitable step on any world that has the right ingredients. This one fact, the speed of life's arrival on Earth, can dramatically increase our mathematical confidence that life is abundant, that it is a fundamental property of the cosmos, not a lucky accident. But then the mirror shows us another reflection. It's a trick of logic perhaps, or a profound truth. It's called the anthropic principle. It reminds us gently that any universe we observe must by definition be a universe capable of producing observers. We are here, after all, breathing and thinking and looking at the stars. This means the laws of physics, the fundamental constants, must be exactly as they are. If gravity had been just a tiny bit stronger, the universe would have collapsed back on itself long before stars could form. If the force that binds atoms together had been just a fraction weaker, the only element in the universe would be hydrogen, and the carbon that forms our bodies would never have been forged. So are we special because the universe was designed for us? Or is it simply that we are the winners of a cosmic lottery? Perhaps there are countless other universes, an infinite number of them, each with different rules. We just happen to live in the one where the numbers came up right for life. It's a difficult thought. Does it explain anything, or does it simply say, we are here because we are here? It can feel like a logical trap, a circle we can't distill. And so these games of probability and logic bring us right back to the central mystery, the one that haunts our quietest nights, the great paradox of Enrico Fermi. If life is common as our first guest suggests, then where is everybody? The silence, that vast, unbroken stillness, seems to offer only two answers, and both of them are staggering to comprehend. The first is that we are rare, perhaps impossibly rare. Maybe the jump from chemistry to life is easy, but the next step is not. Maybe the jump from a single cell to a complex animal, or the jump from a complex animal to a creature that can build telescopes and ask questions, perhaps that step is the great filter. Perhaps it has happened only once in all the billions of years, in all the billions of galaxies. Perhaps we are the first. Perhaps in this entire Milky Way we are truly profoundly alone. If that is true, what a weight it places upon our small shoulders. If we are the only minds in this galaxy, then we are the universe's only way of knowing itself. Every star we see, every nebula that blooms in the dark is seen only by us. We are the consciousness of this vast silent sector of the cosmos. And our responsibility is almost too great to bear. It is to survive, to protect this tiny fragile flame of thought, to carry it carefully across the eons, to cherish our world and each other, because in all this darkness we are the only light. But the mirror has a second reflection. It offers another possibility. What if we are not alone? What if we are not rare and we are not the first? What if the silence is not absence? What if it is just? patience. Perhaps the silence is simply the sound of distance. The galaxy is 100,000 light-years across. A message sent from the other side when our ancestors were first painting cave walls would not even be halfway here. Perhaps the silence is a sign of wisdom. Maybe advanced civilizations learn to be quiet to listen to, turn their attention inward, or to explore realities we cannot yet imagine. Maybe they communicate in ways we cannot comprehend using the ripple of space-time or the entangled dance of quantum particles. Perhaps we are simply a new arrival, a fledgling in a forest of ancient trees, and we just haven't learned how to hear the forest song. If this is true, the silence is not an ending. It is a beginning. It means we are part of something so much larger than ourselves. We are a single note in a galactic symphony that is just beginning to swell. We are not the keepers of the only light, but just one of a multitude of lights waiting to join the chorus. The silence in this case is not empty. It is temporary. This is the final contemplation. The silence of the universe is not a blank, empty void. It is a mirror reflecting our own minds. It is full. It is full of our questions, full of our hopes, and full of all the possibilities we can imagine. It contains our deepest fear of being alone and our deepest yearning to belong. The answer to the Fermi paradox. The meaning of the silence may not be found in our telescopes for a long time. It may be found instead in what we choose to do. In the end, it is the search itself that defines us. It is the act of looking up at the night sky with wonder and with curiosity that makes us human. We are the species that asks, why? We are the part of the universe that tries to understand the whole. The silence is not an answer. It is an invitation. It is the question, and we are the answer that is still being written.